So let's step back from MPC for a second and take a look at the current reality of the non-MPC daily QA. So tests are typically performed in isolation. They're never integrated. They're never comprehensive. You've got your IGRT and 6DOF in one bin, and then you've got your beam constancy in another. And then if you're running SRS, then you probably have Winston-Lutz tests that you perform outside of that. But again, nothing talks to each other. So the question is, what would you want if you had a comprehensive, if you wanted to have a comprehensive program? What would it look like? Well, you'd have your beam constancy, you'd have your IGRT, you'd have your 6DOF in there, you'd have your surface guidance. And notice this is the first time I'm bringing this up in this talk because I think it's a really underrepresented area of daily QA. But then also your isocenter accuracy for everything, and then also an off-axis targeting accuracy for your SRS programs. So the good people at Sun Nuclear recognized this gap, and they decided to come out with the Daily QA4 Pro. So this is the next generation of the Daily QA platform. It's comprehensive. It provides comprehensive and independent verification, combining IGRT, SGRT, dosimetry, isocenter analysis, and more. And you can see here it's put on a 6 degree of freedom base. So let's look at the characteristics and features then. So the physical specs, if you've seen it over there, 30 by 50 by 6 centimeters, so it's a little bit larger than the Daily QA3. It's a little bit heavier than the Daily QA3, but that's because it's got a lot more in it. So on the surface, there are scribed laser alignment marks on the sides and on the surface with a 2 millimeter tolerance at the ends. There's also a scribed crosshair for collimator alignment on the surface and the sides. And there are field size markings for 5 by 5, 10 by 10, and 20 by 20 field sizes with 1 and 2 millimeter tolerance markers on that 20. And then there are 8 symmetric reliefs in the surface that are designed for SGRT. One of the problems that we always have with SGRT is that for flat phantoms, it's hard to get any textures or features so it knows where it is. So if we put on our X-ray glasses and take a look inside, we can see that there are a lot more detectors in this thing. So to start off with, there are 4 ion chambers that are diagonally located here close to isocenter. So these are what's actually going to be measuring your output. And these are good down to a field size of 5 by 5. After that, you start to get partial volume effects, so that's the minimum field size you can do. There are 249 SunPoint 2 diodes in the device, and they're very high resolution. So along the X direction here, they're at a spacing of 2.5 millimeters, going out to a total field size of 22. Along the Y, for the first 10 centimeters, they're on that same spacing, but in the outer 12 centimeters, they go to a 5 millimeter spacing. Along the positive and negative diagonals, you can see what looked kind of like a metal wedge, so this is very similar to your IC Profiler quad wedges. You've got detector spacing of 7 millimeters there, and they actually alternate, so the diodes are under the block and then not under the block, so this way they're able to get a good idea of what the unattenuated profile is, along with those attenuated profiles. And very new are these sideboard left and right diodes, where those are also at a 2.5 millimeter spacing, and these are going to allow us to look at the beam profile coming in from the sides. Next, there are 8 tungsten carbide 3 millimeter BBs that are positioned off-axis in these clear spaces, so there's air surrounding those, so that's easier to resolve them. And each of these BBs has a calibrated offset that comes from the factory to take into account manufacturing tolerances. So it can make micron level corrections for when you're actually using those. And all of this is sandwiched between 1.2 centimeters of solid water for the ion chambers and 1.5 centimeter solid water equivalent for the diodes above and below. Looking at the back of the Daily QA4, we see that there's a recessed lock bar with holes for indexing that it can fit flush to the couch to improve setup and reproducibility. There are tapped corner holes in each of the corners for a gantry mount, or if you want to put leveling feet on it, or if you want to attach it directly to the 6DOF base plate. And there are recessed side handles for easy removal from the lock bar or that base plate. There's a battery capacity, or a battery in this system. It's wireless. It's got 3.3 amp hours, and it gives you about 5 hours of runtime. And it's easily accessible, so when your battery dies, you can replace it yourself. And it's a RRC 2037, and it's about $67 American to replace. And then on the table there, you can see I have the 6DOF base. That's 4 kilograms. It's larger than the Daily QA4. Just so it fits on there, and it's been constructed with inherent roll, pitch, and yaw of 1.5 degrees to get that 6DOF rotation. And this also indexes to the table, and it has what I'm calling a virtual lock bar that you can attach the Daily QA4 to. And lastly, the wireless base station is now powered by the PDI 3.0, and it does not require a power supply. So this is always a problem for us. When we bring it in the vault, we have to find a power supply out next to the physics port, which we never have. So now we don't need that anymore. So let's look at the software that drives this. As Greg mentioned, this is now part of the SunCheck environment, so it's been designed from the ground up to fit there. And you can control it either using the SunCheck Local, where you can put that on a laptop, and it's a complete standalone, or you can integrate this into a larger SunCheck server environment, starting in version 6.0. The local is designed to function very similarly to the server, just with a few features different here or there, reduced. SunCheck Local has a guided setup that walks you through building your environment, so you can make your institution, add your machines, add your daily QA4 devices, and then start building your QA templates and add licenses that you need. And there's a new asset management that's been specifically designed for the daily QA4 because it's very different than the daily QA3. So let's get into how you set up this array then. So there's another guided calibration wizard that walks you through the array calibrations, dose, temperature, pressure, and energy. First up is there a device alignment for accurate setup. So in this module, you shoot a 10 by 10 on the machine, on the daily QA4, enter your couch coordinates, and it will tell you how far off you need to shift so that when you do your normalization measurements, you know that you're properly centered. So very, very helpful. It gets you down to micron level. Next is the array calibration. So the wide field array calibration is gone now. There's no more shifts and rotates and move to A, B, C, E. And now it's a simple file, so you can provide it with a water tank scan at whatever depth you want, or an IC profiler measurement, or a manual file if you just want to fix what the numbers are. However, the caveat is that whatever you shoot that on then has to match that geometry from the scan you took. So if you're using a water tank scan at 10 centimeters depth, you need to have 10 centimeters of solid water on top of the daily QA4. Then there's also dose normalization, and that's going to be field size and energy specific. So you can build them out for each energy and specific to a field size that you're going to use. And you can define a universal one. So if you want to just use one, like the 6MV for all the tests, you can define that as the universal, and it will default to that. Now the daily template creation. So it follows the standard SunCheck process where you build a template, you set your baselines, and then you measure. But there are new template tasks that are specific to the daily QA4 that you can see there on the right. The first is active measurement, which is going to be detector-based, and then the second is imaging measurement, which is image-based. And there are Winston-Lutz tests for both of these image and active measurements tasks. And in those, you can see on the right there, you can choose whether you want to use 4 or 8 gantry angles, and if you want to do couch and collimator as well. And these are completely customizable. You can choose which tasks you want to include. So if you don't want to do couch or you have an ethos and you can't, then you just leave that off. In this QA program, the whole process, the unit, is designed to be done isocentrically, so that you're doing your IGRT and SGRT with your isocenter right in the middle of the device, so you can move directly into the dosimetry. So you're using all those image corrections to get those measurements, and then you can go straight into a Winston-Lutz measurement if you want. And you can do the active measurement one, or you can do an imaging one, or you can do both. It's really up to you. So now let's go into this first IGRT for the position reposition. It's slightly different than the typical daily QA3. So you can put in all the modalities that you have in your machine, completely customizable again, and you can set it up so that the baselines are set to a displacement where you're offset, or to an isocenter position where you're measuring residuals. So this way you can put in an ISO shift, or you can just put in absolute couch measurements and just go to that every day and calculate what your endpoint ones, what your end couch positions are, and calculate the delta there, or just zeros for residuals. And it's very easy to add additional parameters here, where if you want to measure, say, your SSD from your SGRT system, you can just tack that right on in one of these. And so on the top there is an example of what we were doing. So we do our SGRT first, and then KV-CBCT, MV-KV residuals, and then the SGRT residual. And when I started doing this, I was trying to find a point to set up to everything, but in the end, the SGRT worked so well, I just started using that to set the Phantom up and go from there. And so, last for this one, the 6DOF base is optional, but if you include it during this step, that means that the translations and rotations that you applied, they're going to be available now and applied to all the downstream tasks, so the dosimetry and also the Winston-Lutz, which is not commonly done with large rotations like that. So the first thing I wanted to do was evaluate the SGRT, because as I said, we don't really do this currently. So in our Vision RT system, we defined an ROI that covered the entire surface and the edges of the daily QA4. And we did it that way so that we could also track when we put the 20 cm electron cone in, so it still detects it and it doesn't cause problems with the system. So we tested this over the full range of motion, all the axes on the couch, and we saw that the maximum translation range that it could detect was up to about 4.5 centimeters on the lat and long, and vert from 13 to 17, so very wide on the vert. The pitch and roll, we tested the limits of 3 degrees 3 millimeters and also 90-degree couch rotations, and it accurately, it matched them perfectly. But of note, because of the symmetric relief pattern, the offsets tend to start to get wonky and zero out once you go at that 4.5 centimeters, because it starts to see the recessed values as as the adjacent one. And similarly, when you start to rotate the couch to 45 degrees, it starts to think it's centered again because it's, again, symmetric. But the system detects that, the couch, when it's supposed to go to 90, so it knows that. But last part on this is that this is a test that I believe this is the first time we'd ever actually run this and really compared our SGR system with couch rolls and all that to our image guidance system. So it was very, very helpful. Now let's move on to the dosimetry tasks. So you can notice many of these parameters are carried over from Daily QA3, like the output, profile constancy, the field size and shift, and the flatness and symmetry. But the difference is now you're able to measure at a much wider range. So you can measure anywhere from 2 centimeter to 20 centimeter square fields. The output is still, the minimum you can do there is a 5 by 5, but you can now measure all these profile parameters for those. There are new metrics now, the penumbra, the beam shape constancy for the triple F fields, the beam center, DPSI, which is measuring at specific points along those axes, and also the dose per pulse. And the energies for both the electron and photon are actually using those attenuating wedges on the diagonals, similar to the IC profiler. So there's also a new dose output correction factor, so for when you need to move this device to measure on a different unit. So there's always a problem with the Daily QA3 when you have to try to move device to when another one goes down, and you always end up getting wonky results. Now you can account for that directly during your measurement. The Daily QA4 also has new features. Automation, where you can auto-advance, true auto-advance, where you click start once and it will carry you all the way through and you don't have to touch any of the measurement space in SunCheck. And this works because it has a built-in trigger, not a software trigger, where it can detect when the beam turns on and off to tell you to move to the next one. There's also a field size detection, which I found to be very useful. If you forget to retract MLCs or something, it will tell you, say, hey, you did something wrong here. It's the wrong field size detected. And so the automation in this trigger really allows for one-click execution for all of your beams and energies. So we did some quick analysis here, a quick assessment, so measured on 6 Linacs around 30 sessions. And what I didn't show before was that they want you to define the field size with MLC, but I've always done jaw, so I had to prove to myself that you could do that. And so we measured for both jaw and MLC on all these measurements. So we saw that the output factors are consistent down to about 7 millimeters, after which point the MLC gives slightly higher output factors. And a little bit hard to see, but for the beam profiles, we saw the largest difference in very small fields for flatness and symmetry, where the jaw had a much wider distribution and a much larger bias for those 2x2 fields. And in the penumbras, it's very interesting because you can kind of guess what was going to happen based on the geometric penumbra, where the MLCs are closest to it, so they should have the smallest penumbra for the Y, which we see is the case. However, in the X, it's not quite as good because of the rounded leaf edges. So in that case, the jaw is actually a little bit better because it's not as far away as the Y as well. But again, and there's also, you can see that the penumbra in the Y had a slight discontinuity at that 10 centimeter point, because that's where it switches from the high resolution diode spacing to the lower resolution 5 millimeter. So now let's talk about the active measurement Winston LUTs. So this uses measurements for gantries at either 8 or 4 fields, includes the collimator and couch, but they can be measured independently. And this is going to use both the X and Y diode array and the lateral diode detectors to measure the field center. The gantry requires field size defined less than 2.5 centimeters, and the collimator and couch can use either anywhere from 2 to 10 centimeters. And on the left there, you can see this is what it looks like when you mode it up on TrueBeam, and you can turn the automation on, so it will run through all of these fields for you, except for the couch ones, which you can move remotely from outside. And on the right there is what the actual acquisition looks like in SunCheck. And on the bottom here, this is just a little movie showing what their automation looks like, where you just hit play, in the top left there, and it will automatically step through everything. So you can basically hit play there on SunCheck and then start on the machine, and then you don't touch anything again until you get to the couch where you have to move the couch from the console. So one of the best parts about this is that now it actually combines that previous position reposition with this active measurement Winston LUTs, so that you can actually see all of these together. You can see all of your imaging systems along with your Winston LUTs. And you can choose to see what your measured value was. You can remove the positioning error that you might have had in residuals, and you can compare this to a baseline if you want. So you can go through each one of these different systems and just see what the isocenter contribution is. And you can do deep dives by hovering over and turning them on and off to really drill down into what is a rate-limiting step for performance. And so we measured this one as well. I did 18 measurements across 6 machines using the John MLC again. And we saw that the MLC is much, much tighter on all of these, and there's less bias. But we saw that there was a little bit of a bias in the Y direction. And I think that's because that's our lowest resolution direction, where that's using our CBCT slice thickness of 2 millimeters and the planning slice thickness of 1.5. So it's really hard to perfectly identify the correct positioning of the isocenter in your plan. But this is something that you could actually remove out by using a baseline and not just setting it straight to 0. And the big question is, but does this actually work? And so what I did was I pulled 2 years worth of our Winston LUTs tests across all of our machines. I pulled all of our MPC results, and then I compared it to the 18 measurements that we've taken so far. It's still a little bit early to say, but it's on par. It looks commensurate with that. So there's no real gotchas or concerns right now. So I think with a little bit more data and a little bit more refinement in our process, so you can probably get it a little bit closer. So now let's talk about the active imaging Winston LUTs. So this is similar, only it's now going to use the imager panel. So it's 4 or 8 gantry angles and 2 MV acquisitions for both the couch and collimator. And the KV is also going to require 8 exposures, 4 or 8 exposures. So each of the MV MLC images cover the tungsten target with a 2x2 field. There are also some larger MV open sections that are used for scaling, orientation, and alignment. Unfortunately, delivery can't be automated because of the attached integrated imaging, so you have to go through each one step by step. And when you actually go to analyze these, it requires manual image upload and association. Hopefully that's something that they'll automate in the future. So on the right is what the images look like of all the ones that you'll take for this. And I should point out that you can actually automate this in developer mode. I've written the script that actually does it, and it really improves the speed on this. So let's just get into the results. So this is for the KV, what that looks like. So for each gantry angle, you're going to have the image fiducials that are detected, and they're compared to their expected values. And again, that's with that calibration applied. And you're going to get calculated values for the gantry angle, the pitch, the roll, the KV image panel offset in X and Y, the rotation of the panel, and the SID. And you can see on the right there, that's what that looks like comparing to baseline, and also on the bottom there, a deep dive where it shows the detected fiducial positions and what their differences are. So all of these are then combined to give you a phantom position that's calculated on those images. For the MV and MLC results, again, for each gantry angle, you're going to have the fiducials that are detected, but you're also going to have calculations then for the gantry angle, pitch, roll, your MV image panel offset and rotation, and also SID, your MLC field center, field size, and the field fiducial offset in X and Y. So this is the part that's going to be very similar to your multi-met Winston LUTs, where it's doing their field target coincidence. So you're going to have that for each angle and for each fiducial, so 64 combinations, so it's going to be a lot of data. And so these are just some of the deep dive plots that show the analysis behind the scenes. And this is all summarized then to report what the maximum error was in any one of those parameters across all the gantry angles. So it'll tell you which gantry angle was the worst and what the value was. And not shown, but this can also be put together in those rows plots, similar to the active measurement that I'm sure you can see in a demo. So this is great, but it looks like a lot more work. So I did an efficiency analysis and compared it to our current state. So in our current state, it takes us about 16 minutes to get through our daily QA3 and IGRT tasks. And with the daily QA4, because you're not going in the room and coming out and doing multiple setups, we actually cut about 5 minutes off that time. For MPC, just running the beams and the outputs, that takes us about 4.5 minutes, a lot of which is time spent loading it. When we add the Winston-Lutz, if we were just to do a cube Winston-Lutz in our current program, that doubles the time now to over half an hour. However, with Daily QA4, you only add 5 minutes, and it's a very simple setup that your therapist can run as part of their morning QA. There's no complicated setup that they have to do. It's already done. With MPC, it adds about 5 minutes then with doing the geometry test. And if we want to do the big one, where we're doing off-axis Winston-Lutz, doing the multi-met Winston-Lutz right now adds even more time, so we're up to 37 minutes, whereas in the Daily QA4, it only adds a little bit more. And in that test, you're getting so much more information. And on the enhanced couch, that adds about 7 3/4 minutes. And if you remove the couch rotations from any of these, you knock off about 3 minutes of time. So overall, it takes about the same amount of time, current state, as it would to do the Daily QA4 with that active measurement Winston-Lutz. You would be gaining all this information basically for free. And the Daily QA4 is the only one in this plot here that's assessing SGRT. So in conclusion, the Daily QA4 integrates IGRT, SGRT beam dosimetry, and Winston-Lutz verification into a single device, enabling comprehensive Daily QA in a single setup and session. It really consolidates a lot of phantoms that you might not need anymore. The base plate enables full 6 DOF image-guided corrections prior to all measurements, so that you're reflecting true machine performance and without setup error in clinically realistic scenarios of rotations. The active measurement Winston-Lutz are commensurate, the results with MPC and our traditional Winston-Lutz. The active imaging Winston-Lutz provides a full picture of the phantom positioning, the panel performance, gantry performance, and also on your targeting accuracy. So this is kind of a combination of multi-met Winston-Lutz and almost the ISOCAL verification with the amount of information it's giving you. There are significant workflow efficiency gains where the current state reduces it by about 5 minutes, and adding that Winston-Lutz adds 5 more minutes back, so basically more testing in the same amount of time. And this provides an independent, interpretable alternative to vendor black box QA systems with comparable ISOCenter and imager tests, superior beam quality constancy tests, and covers QA and clinical ancillary systems that the vendor platform can't do. So that is now all that I have to go over. I'd like to thank the NYU Langone team that helped with a lot of the measurements for some of this stuff, as well as the Miriam S&C team, especially Raj, who helped design the Daily QA4. It's his child, and Amanda. All right, thank you so much.